Let's start with strings. Again, you take a rope like this, a string, and you attach a weight to it. How much tension in that string? Notice that string is tight when you pull on it. What's that tension? Or you're pulling a car, so your friend's car broke down, you take a rope, you tie it to the car. Don't recommend that. You tie this end to your car and you drive and you pull the car behind you. What's the tension in that rope there? So let's talk about tension in a string. We'll start with that one first. String, rope, whatever you want it to be. Let's say this is the ceiling here. In the ceiling we have a hook, and in it we take a rope, and the rope is attached to a box. There's a box. Let's give the box a mass, I don't know, 50 kilogram. Or maybe, we don't want to talk about hunting. I know some people like to hunt. That's not me. But you got a deer, you want to gut the deer, you hang the deer now, and it's dangling from a string there. What is the tension? How much tension is by that string, by that rope, to hold that box from falling down?
The weight plus the gravity?
Yep, well let's look at what's acting on this box. What do we have? You're right. So we have the weight of the box pushing down, which is mass times gravity. The mass of the box is 50. Gravity is what? 9.8. Is that 490? And why isn't the box falling down? How come the box didn't just collapse or come down? What's keeping it from falling? The rope and the ceiling. So that rope actually is pulling up, we'll call T for tension. It's pulling upward. What about, is there a normal force here? No, because the box is not sitting on a table or the ground. If it was sitting on the ground, then the ground's pushing up. That's your normal force. So there is no normal force here. The only thing I have is the tension, the cable, the string pulling up, and I got the box dangling down. Again, just like if I attach this one here. There we go. Attach this weight, and I'm holding it. The reason this is not falling is the string pulling up on it. There's no normal force. So these are the only two forces. If the object is not moving, if you think about it, if the object which is not moving here, your velocity is zero, your acceleration is zero. Well, if the acceleration is zero, Newton's second law says what? The net force equals mass times acceleration. And if your acceleration is zero, it says the net force will have to be the mass times zero. It doesn't matter how heavy the object is. The net force is zero. How can the net force be zero? That means if you take all the forces, if you add them all, the ones pointing upward should equal all the forces pointing down. They have to be. They have to cancel each other out for the net force to be zero. So what do we have pointing upward when you look at that picture? Tension. And what do we have pointing down? The weight, which is mass times gravity. So the tension is equal to the weight. That's how much tension in that string there. Is the tension always equal to the weight? The answer is no. Let me give you another example. Let's say you want to lift a box up. It's a heavy box. Again, there's the ceiling. But now instead of having a hook, let's put a pulley there. So we have a box that has 100-kilogram box, and the pulley now is attached, and people pulling in this direction on it to make it move up. So I get a couple of people on this end pulling on that rope to make this one move up. So this is going to move up an acceleration of 2 meters per second squared. So I got a couple of big guys here. Say, hey guys, can you help us lift this box here? And they start pulling on that rope. Well, let's look at this. What do we have? We have the weight down, which is what? Mass times gravity. What else we have? We have the tension up. That's the string pulling on the box, moving upward. That tension, by the way, is this tension here. Same tension, which is the same as this force, right? These guys here pulling on it. In that rope, as long as the rope is tight there, it's not saggy. When you're pulling a car behind you, if the rope is like this, forget it. But when the rope is stretched and it's tight like this, the tension this way is equal to tension that way. For every action, there's an equal and opposite reaction. So now we look at this box. It's moving upward. So Newton's second law says the net force equals mass times acceleration. Well, the fact this is moving upward, what's the net force? What do we have for net force? What is it? 200. 200? What is it, 200? No, that's the mass, right? The mass is 100 kilogram. The weight is 100 times 9.8. That's 980. That's the weight. But which way this is moving? Upward. So what's the tension? What's the tension in the cable? Can we figure what that is? Well, this box is moving upward. If it's moving upward, that says this force has to be bigger than that. The tension has to be bigger than the weight. If it's moving down, the weight is bigger than the tension. T minus the weight equals the mass times acceleration. T is unknown. The weight is what? 980 equals the mass times the acceleration. The mass is what? 100 times the acceleration, which is 2. T equals what? 1180. Notice if this object wasn't moving, the tension will equal to what? 980 if it wasn't moving. But when you start to move with acceleration there, the tension on the cable is more. That's why if a cable is going to snap, it's not when you just attach the weight like this. When you give it that acceleration, because now you're adding more tension, especially when you snap it really fast. The reason? That acceleration will not be 2, it will be a lot more than 2. And if this number became 4 here, you're adding what? This becomes 400. That tension increases to a larger value. So on these belts, you don't want that to be moving really fast at large acceleration. You want to move at constant speed. If it moves at constant speed, that means your acceleration is what? 0, and the tension equals the weight. You do not want that elevator to go from 0 to 15 miles per hour like in 1 second, because if it does, that cable actually holding that one day is going to snap. because you're putting so much tension on it. So slowly, we'll start slowly. This way you're not adding to it. The tension is going to equal to the weight. Yes?
You're saying that if you put it at a constant speed, it's going to equal to the weight.
Correct. At constant speed, that means your acceleration is equal to zero. It's the change in velocity over change in time. If your speed or velocity is not changing, your acceleration is zero. If your acceleration is zero, the net force equals mass times acceleration. And since the acceleration is zero, the net force will equal to zero. The net force is T minus the weight. So in this case, if you move in this at constant speed, the tension in the cable will be 980 Newton. Tension is a force, so the unit is in Newton. But when you move it up at higher rate, like acceleration of 2, then notice that the tension in the cable increased. I'm trying to give you some application where tension is. One of the things we're going to do in the lab upstairs this week, today or tomorrow, depends how we're doing on time, is actually we're going to take a glider it's sitting, this is a glider, frictionless glider, there's no friction yet. We'll add friction later, a table like this. On it, we're going to take some weight here. It's sitting on the table. But there's no friction again. So if there's no friction, that acts like it's floating, but it's not really floating. There's a pulley here, and this goes over the pulley, dangles down. Let's say I put I'll put 10 kilogram here, and I put half a kilogram here. If there's no friction, if you dangle a dust, that's the string. I'm neglecting the mass of the rope there, or the string. So this is a pulley here. Assume the pulley is frictionless too. There's no friction in the picture. If you attach a dust there, that thing will move. If the table is leveled, any little weight you add there, if there's no friction, that thing will move. This will move in this direction, and that will move in that direction. And the question I have, can you find the tension in the string, that's this tension, which is the same as this tension? Notice the only reason this box is moving because the string is pulling on it. That string is pulling to the right. The only reason this is not falling like gravity, like this, to the ground is what? Because that string is keeping it from falling hard. Slowly, it's going to glide down. And these two have to be equal. Why? For every action, there's an equal and opposite reaction. If the string is pulling this way, it has to be canceled by that one. So find the tension and find the acceleration. Both of these are going to be moving at the same speed, the same acceleration. So this one is not going to have a different acceleration than this or a different speed. How do we find these two? Well, let's look at each box and see what we have. Let's look at the 0.5 kilogram. Let's list all the forces acting on that 0.5 kilogram. What do we have? The weight down, which is mass times gravity, and that's 4.9 Newton if you do the math. 0.5 times 9.8. What else we got? We got the tension up. And which way is it moving? This one. moving down. If it's moving down, that tells me this force has to be larger than that one. If it's moving down. So the net force, Newton law, says the net force equals mass times acceleration. The net force for this is what? The weight minus the tension. It's this minus that. Equal the mass, 0.5 times the acceleration. How many, well, do we know what the weight is? Before I say how many unknowns, do we know what the weight? 4.9 minus t equals what? 0.5a. So how many unknowns in this equation? 2. I can't solve it. I need another one. Let's look at that one. $10 kg. What are the forces on it? All the force on the 10 kg. What do we have? The weight, okay, the weight down, which is mass times acceleration. 10 times 9.8, that's 98 Newton. What else we got? Tension is going that direction, okay. What else? Yep, the normal force pointing upward, good. And since this block is not moving up or down, that tells me the normal force has to equal to what? 98 Newton. And which way is it moving? That's the direction it's moving. So what is the net force in the direction it's moving? We don't care about the other direction. In the direction that you're moving, what is the net force? What is it? T minus. Why weight? In this direction, what do we have in this direction? In this direction, left to right. N is up, has nothing to do with this direction. The weight has nothing to do with that direction. So the only thing we have in this direction is the tension. That's it. There's no subtractions from it. That has to equal the mass, which is what? 10 times A. Now here's another equation. How many unknowns now we have? We have 2 equations by 2 unknowns. Now can we solve this? The physics is over. Now it's math. Yeah, we use substitution. 4.9 minus t. What's t equal to? 10a equals 0.5a. That equation. I took the t here and plugged it. I put 10a here. 4.9 equals what? 10.5a. What's a equal to? 0.47 roughly meters per second squared. Can we get what the tension in the spring is? What's the tension? It's 10 times A. Or I can use that one. This is easier to use. Might as well use that one. Either one will give us the same answer. But since this is easier, I'll use that one. 10 times 0.47, which is what? 47 Newton. So the tension in that string is going to be 47 Newton.
4.7.
Is it? Yeah, that's what I meant. There we go. It is 4.7. Thank you. Where's the other half? Where's Kendra?
She said she's not coming.
She's not?
Yeah.
Uh-oh. Let's modify this. Let's put more, make it more challenging. We keep adding to it. Let's combine some of the stuff from here with the last two chapters. Let's say we have a table that looks like this. This is my table. This angle is 70 degrees. This angle is 25 degrees. I'm not saying this is 90-degree angle. I don't really care if it is or not. It's not important to me. Because I know some of you are thinking, wait a minute, some of the angles in a triangle should be 180. That looks like 90 degrees. No, it's not. It could be any angle here. So I don't care about that angle. There's a pulley here. Let's put a 10 kilogram here. That's 10 kilogram. The string, there's a string that goes over the pulley and it comes down this way. And let's put another weight here, some mass. Let's put a 5 kilogram here. Smaller one. Again, assuming no friction. So I write that no friction yet. We'll put friction later. Question number 1. Will the system move? So you hold them, then you let go. And now, would it go this way, this one will go down and that's up, or would it go down this way and that's up? If yes, we'll go here. If yes, which direction? And 2 again, if yes, if it moves, find the tension in the cable and find the acceleration. So it's better for us if they don't move. I don't have to do anything if they don't move. Oh, perfect. Nothing's going to happen. There's no tension. We can find the tension, but no acceleration, less work. Now the logic reaction, people say, oh, it's going to move this way. Why? Because that's heavier. Well, not really. You can't go by the weight. Let's list the forces acting on that. We have the tension this way. And that's being canceled with the tension that way. We got the normal force for this one. We'll call it N1, normal 1, because there's 2 of them. And we have the normal force here, N2. What else we got? The the weight of this and the weight of that. But remember, I'm going to break the weight down to two parts. We said we're going to break the weight into a component in this direction, a component in that direction. In this direction, it's mg sine of theta. In this direction is what? mg cosine theta. Let's plug in the numbers. That's 10 times, that's 98. 98 sine of 25. That's equal to what? 41.4. And the other one is 98 cosine of 25. I think I wrote 25, not 45. 88.8 here. Same thing right here. It's absolutely the same thing. mg.
Well, doesn't the normal force have to be 88.8?
Yes, for this one?
Yeah.
Yes. 88.8. Very good. Why? Because the object is going to slide this way. It's not going to move up and down. So these two will have to be equal. Let's look at this. mg sine of 70 degrees. Because the angle here is 70. Here was 25. So that's 49 sine of 70. 46. And we have what? mg cosine of 70 degrees here. So here the sine was what? 25. I just put, since I put numbers, might as well put numbers here. Try to make them the same. And what's mg? That's 49 cosine of 70. 16.8. So what's the normal 2 equal to? 16.8. Now, are these two numbers the same? If they're the same, the system is not going to move. Are they the same? No. Which one is bigger? 46. So it's going to move in that direction. Got a bigger force pulling in that direction. So this actually will move down this way. And this will move up. If this one moves down, it's going to drag that to go up. Again, the reason it moves down, this number 46 is bigger than 41. So since 46 is greater than 41.4, the system will move to the right. To the right. It's going to go this way. Again, let's look at each one and write an equation for them. This is the 5 kilogram. We got the normal here, which is 16.8. We got this one, 16.8. We got the tension going up. We got 46.0 coming down. It's moving this way. So what's the net force in that direction, the direction you're moving? Because Newton says if you move in, there's a net force equals mass times acceleration. What is it?
It's weight minus.
Well, it's not the weight, it's the 46. Yep, minus t. So 46.0 minus t is equal 5 times acceleration. How many unknowns in that one? 2. Now let's look at that one. The other one, let's draw that picture here. It looks like this. 10 kilogram. We have T up there. 41.4 down. We got the normal force, which is 88.8. And we got the component of the weight in this direction, which is 88.8. And which way are you moving? You move in that direction. Again, Newton's second law, the net force equals mass times acceleration. What's the net force? Yes, it's this minus that. Notice these two, you're not moving in that direction. They don't come anywhere in the equation, only in this direction. T minus 41.4 equals the mass, which is what? 10 times A. Again, how many unknowns do you see there? 2. The physics is done. Now it's the math. We get 2 equations but 2 unknowns. There's my 2 equations. How are you going to solve them? I can use substitution to solve for 1, right? So if I solve this for t, it's going to be what? 10a plus 41.4 if I solve it. Move the 41.4 to that side, becomes a plus. Now we take this equation, the top one, which is 46.0, minus t. In place of t, let's put what? 10a plus 41.4 equals 5a. .0 minus 10a minus 41.4 equals 5a. Move the negative 10a to that side, becomes a plus. What's 46 minus 41? 4.6. .31. That's my acceleration. If I know the acceleration, can I calculate the tension in the rope? It's 10a. I can use either equation, but that's an easy one since I already have a. 10 times 0.31 plus 41.4, 3.1 plus 41.4, what's that, 44.5? That's the tension in the string. I can make thousands of applications of tensions here. Now, we didn't even bring in friction yet. I can bring in some, I don't know if there's a whole section on friction or not. My machine kicked me out, already timed out for not using it. But let's put some friction and see what happens. You take in your nephew, niece, you have a little toboggan here, you're going to take them sledding. Oh, it's dirty now. So this is that sled there. And there's your nephew and niece. We'll put two of them there. And you're pulling with the rope in that direction. We'll say 100 Newton. And the angle that you are pulling with is 22-degree angle. So let's find the tension in that string or in the rope there, and let's find the acceleration. The only thing I have to give you, because there's a friction here, and you're moving, let's say mu k equals 0.2. The coefficient of kinetic friction is 0.2. That's between the snow here and the sled. So let's look at this and write all the forces acting on it. Let's see if you remember. You have the tension, the string. You're pulling on that string in that direction. Oh, I drew it the wrong direction already. Which direction? And what was the angle here? 22 degrees, right? What else you got there? The friction. Which way the friction is going to be? To the left. Why to the left? Because you're going to be moving which way? To the right. So SFK, kinetic friction. What else we got? I forgot to give you something. Let's assume the mass of the two kids in the sled is 40 kilogram. So what else do we have? The weight. $392, is it? What else do we have? We have one more force. What is it? Normal force, yes. The ground pushing up on it, the snow. Is the normal force equal to 392? To that number? What do you think? Why not? Friction is that direction. Are they equal? I'll say no.
No, because the tension is pulling at an angle.
Yep, because the tension is on an angle. We're going to take that tension, break it down to x and y value. That's your free body diagram. So let's see. So I'm going to take this tension here, and break it down to two components, one in the x direction and one in the y direction. The one in this direction is going to be t cosine 22 degrees. The one in this direction is going to be what? T sine 22. So how do you know it's going to be up? Because to go from here to there, you have to go to the right and go up. So to the right and go up to go from here to there. What else we got? We got the normal force. Yes.
From comparing from the other problem, it's only when it's slanted or like an incline that you switch the cosine and sine.
Correct, because the angle there was given with respect to the y-axis, here with respect to x.
Okay.
See that angle? The question, like in the previous example, when we did this, I use sine here and cosine there, because that angle really is with respect to the y-axis. You don't see it here. But if I drew the line, if I drew the weight down and make this my y-axis, that 25 is the angle between the y-axis and the weight. That's why. And the kinetic friction is going this way. Which is, by the way, mu k times n. In which way the object is moving, or the sled is moving with the kids in it? It's going to move to the right. If it's moving to the right, that tells me this force has to be larger than that. Now, I assume it's going to move, but I might be wrong. Maybe 100 Newton wasn't really strong enough to move it. I might have to change it. Now, was the sled bouncing, going up in the air and into the snow up in this direction? Was it moving? That tells me the sum of the forces pointing upward should equal the sum of the forces pointing down. What do we have pointing upward? We have the normal force. Add to it t sine of 22 degrees should equal the weight, which is what? 392. The normal force, 100 sine 22 equals 392. What's the normal force? So notice it's not the weight. It's 392 minus that number. (100 sine 22). 354. What about in the x direction? It was moving in the x direction, right? It was going to the right. Since it was moving to the right, then the net force equals mass times the acceleration. Here's my picture. To the right, the net force, this one minus this one. You're going to the right, so it's this minus this. T cosine 22 degrees minus mu k times n equals the mass times the acceleration. What was the mass? 40 times the acceleration. T is what? 100 cosine 22 minus mu k, which is what? 0.2 times the normal force. We just finished calculating. What was the normal force? 354. 354.5 equals 40A. (100 cosine 22 minus, I'll do the whole thing, 0.2 times 354.5 is 21.8 equals 40A. What's the acceleration? Divide by 40.55 meters per second squared. So that's strings. I'll take a break from there. I'm not going to stop the video. But there were strings and springs. Let's look at springs. Let me log in the computer. Maybe I'll do one more example, just got my attention. In the hospital, sometimes somebody will break their leg and they go, oh, they put this contraption. Or you see people sometimes break their neck and they go, well, we need to keep you in this position for a couple of weeks to make sure the bone heals. So this person broke his leg, and this is what actually they did. This is the foot. They attach this contraption here, and your foot is right there. They take tape and wrap it around it so it doesn't move. Then they have a little pulley here. They have a rope going up this way into another pulley here, and the rope goes into the ceiling, attached to the ceiling. It doesn't move. On this end, they get another pulley here, and they dangle a weight here to keep the pressure off your foot, keep you pulling in that direction. And let's assume these angles here, 40-degree angle. Now, I'm not really sure if the tension in these cables is the same or not. So I don't want to make an assumption they are the same. I'll call them T1 and T2. Now your foot, what is your foot doing to that? Now this one wants to move that way. The weight's going to pull on your foot. So actually your foot is keeping this pulley from going that direction. It's pulling on it. Otherwise your whole body will slide in that direction. We're not putting a lot of weight. If you attach a lot of weight, trust me, you will slide down. And to give you some numbers, let's assume this person was pulling with the force of 165 Newton in this direction. That's the force. The question is, what's the tension in the cable and how much mass I need to attach here? That's your job. You're the physician assistant. You have to figure out how much mass to attach there. Find the tension, T1 and T2, and the mass. How much mass should we put there? Let's deal with T1 and T2 first. This got my attention there because it deals with health field. A lot of people who are actually pre-med students, they take physics. Why am I taking physics? You know, for a problem like this. So let's look and see what we have. So you'll have a little understanding what's going on there behind the math. You get the person, you want that force to be pulling in this direction of 165 Newton. And again, I'm not sure if these two are equal or not. I can tell you if the angles are the same, like in this case, they'll be equal. But we'll prove that. We get T1 in this direction at 40-degree angle, and we get T2 at 40-degree angle here. So I'm looking right there at this spot, at the foot. What are the forces on the foot? Or on that pulley there, right there, which is attached to your foot. You get this one pulling up, this one pulling down, this one pulling backward. I'm going to take these two and break them down to X and Y components. Always. So let's see what my X and Y component. Oh, my hands are all black now from the markers. Here's what I have. I have the 165 going this way, Newton. This T1 is going to have a component in this direction. T1 cosine 40 is going to have a component going upward. T1 sine of 40. To go from here to there, you have to go to the right and down. So this is going to have a component this way. T2 cosine 40 and T2 sine 40. Now we're hoping by putting this contraption that the person's foot doesn't move. Stable there. I don't want it to move. I'm trying to stop it from moving so the bone will heal. Well, if it's now moving, that says what? The force upward should equal what? The force down. The foot is not moving. Sum of the forces pointing upward should equal sum of the forces pointing down. We have an equilibrium, balance system. What do we have pointing upward? T1 sine 40. What do we have pointing down? T2 sine 40. If you divide both sides by sine 40, what are you going to have? T1 equals T2. When the angle is the same, the tension will be the same. If the angles are different, then the tension is not the same. Because sine 40 and sine 30 is not the same. You can't cancel them. Again, the foot wasn't moving in the x direction. If it's not moving, it says if you take all the forces pointing to the right, add them all, should equal all the forces pointing to the left. Add them all. what do we have pointing to the right? We have what? T1 cosine of 40 plus T2 cosine of 40 equals 165. Since T1 is equal to T2, I'll just call them T. There'll be two of them. Can we get what T1 and T2, which is the same as T? What's that? 165 divided by 2 cosine 40. 165 divided by 2 divided by cosine of 40. I get 107.7. So T1 and T2 both equal to 107.7. Nope. Even, that's the unit. That's not a factor here. That's the unit. So we answered 2/3 of the question. What's T1? What's T2? How much mass should I attach here? Well, guess what? If this is T2, what's this one? This is also T2. For every action, there's an equal and opposite reaction. This is not moving. We have the weight down. Well, if this one is not moving, why is it moving? Because these two are equal. T2 has to equal to mg. So T2 equals mass times gravity. 107.7. I'm looking for the mass. Gravity is 9.8. How much mass I need to attach? About 11 kilogram, 0.99. So we need to attach 11 kilogram, roughly 24 pounds, to make sure that foot stays there and the pressure or the tension in this direction is 165. Again, the way we find that, if this is not moving, that means this has to equal to that. You only get the weight down, you get the tension up. And they have to be equal to each other. I'll stop this video and I'll do the spring on the other one. It's too long of a video.